Hello everyone, welcome to the Baselab Sensor Fusion How-To video series. Today I'm going to show you how to deal with different sensor latencies in the sensor fusion. This can happen, for example, if we are going to fuse a camera system with a radar device and one of these sensors provides measurements that arrive too late compared to the other one. In this video, I will talk about several possible solutions. A multi-sensor data fusion system processes measurements coming from various sources and with different latencies. The delay can be caused by data preprocessing, such as the object detector inside a smart camera. Sometimes the delay from a certain sensor is noticeably larger than the others. From the sensor fusion's point of view, the measurements are now received out of sequence. For example, we have a simple system consisting of a radar and a camera. The radar provides 6 measurements and the camera has 3. According to the time when they are measured, or the so-called measurement time, they should be input to the sensor fusion in the order from 1 to 9. However, because of the large delay in the camera sensor, measurement 3 arrives later than the measurement 4. We can identify this if we lay out their so-called arrival times on the time axis. The 3 and 4 are now out of order. Measurement 3 is a so-called out-of-sequence measurement, or OSM. If the out-of-sequence measurements are not handled properly, they will lead to degraded fusion results. Because now, the sensor fusion will process outdated observations of the environment. Untreated OSM can be considered a systematic modeling error. So, how do we handle OSM? I am Liang from Baselabs. In this video, I will show you how Baselabs Credit Embedded deals with out-of-sequence measurements. I will stick to the one radar, one camera system as an example. First, I will show you what will happen if OSM occurs but not addressed at all. In the next setup, I will demonstrate 3 possible solutions, including the built-in capability of Baselabs Credit Embedded to handle this issue. Baselabs Credit Embedded is software for the efficient development of series-grade object fusion systems. Prototyping with Baselabs Credit Embedded involves the usage of a backend and a front-end. The front-end allows the user to register sensors and configure their characteristics in the graphical user interface. The backend has a series-grade implementation of a rich set of sensor fusion algorithms, which will be used by the front-end according to the configuration. Baselabs Credit Embedded is designed to be able to cope with various sensor modalities, different sensor latencies and frequencies. In another how-to video, different sensor modalities are discussed with a more general aspect. Today, I'm going to focus on the sensor latencies and the consequences if they are combined into one unified checklist. Practice reveals that sensor latencies are inevitable for real-world systems. Different delays in different sensors will create out-of-sequence measurements. If not handled correctly, this OSM will cause serious issues. We have at least 4 options to deal with them. The first option is to simply ignore any measurement that is out of sequence. The second option still uses the out-of-sequence measurements, but only after modifying their timestamps, such that they appear in sequence at the data fusion system. Third, we can employ a buffering mechanism inside the data fusion system to ensure sequential processing despite potential out-of-sequence arrivals. Fourth, we can use a fusion algorithm that supports visual diction for multi-object tracking. In this video, I will show you the first 3 options. Let's recap the OSM solution in this 2-sensor system. The camera measurement 3 and 6 are now out of sequence. Now let's take a look at the first solution. As shown here, measurement 3 and 6 are simply ignored and not input to the sensor fusion system. This will not trigger an OSM issue, but at the risk that the environment model might not be updated by the particular sensor for a long time, especially if that sensor is systematically delayed. The sensor fusion would be partially disabled for this path. Now let's try the solution that modifies the timestamps of an out-of-sequence measurement. And this can be seen here. Despite a late arrival, the measurement time in measurement 3 and 6 are now modified to avoid OSM issue. This surpasses the issue but makes the sensor's observation inconsistent because now we have artificial measurements. When talking about consistency, not only the sensor's observation but also the time when the observation is made is critical. Inconsistent sensor observations will cause degraded performance and even numerical instability of the whole system. To compensate for artificial wrong timestamp, a possible workaround is to increase the assumed measurement noise of the sensor. Even though this will help, the algorithmic performance of the whole system is not optimal. Baselabs Create Embedded provides another solution with a so-called deterministic buffering approach. In this example, we will need to manage two buffers, each for one sensor. The sensor measurements will be first kept in the corresponding buffer before they are processed by the sensor fusion, as we can see here. Each time the system wants to process any measurement, both buffers will be checked to ensure that always the oldest measurement will be taken out of the buffer and processed. Let's take a look how the measurements are buffered and processed. Here we let the sensor fusion system try to process any pending measurements each time a new measurement arrives. Maybe you have noticed that the consumption of the pending measurements remains possible as long as none of the buffer is empty. Because facing an empty buffer, no one can foresee whether the upcoming measurement is an out-of-sequence measurement or not. To show the result with different solutions, I have configured the example 1 Radar 1 camera system using the Data Fusion Designer, which is the front end of Baselabs Create Embedded. Here you can easily verify the sensor's field of view. By clicking on the button Generate Data Fusion, I have now got the code that can be built into a sensor fusion library according to my configuration. After that, I'm going to start a built-in test environment, the so-called replay. You can read recorded measurement data from files and input them to the sensor fusion library. The fusion result is shown in the bird's eye view, which is a built-in visualization. For more detailed explanation of Data Fusion Designer, replay, and visualization, feel free to check the other how-to video. I'm now showing the fusion result of a test drive on the highway with in-sequence measurement data. This gives me a baseline. Now we will run the system with the same data, but the camera measurements have now a systematic delay of 200 milliseconds. That is, the time between the physical observation of the sensor and its arrival at the data fusion system is now 200 milliseconds longer than the baseline. Consequently, camera measurements created earlier will arrive later than some radar measurements, so we have out-of-sequence measurements. Baselabs Create Embedded treats any out-of-sequence measurements as an error. When I start the replay now, as you can see, I get immediately a runtime error. According to the manual, this error code indicates that an out-of-sequence measurement was detected by the sensor data fusion system and the shutdown was triggered. I want to bypass this error with solution number 1, to ignore the out-of-sequence camera measurements. As you might have guessed, the system is running, but now I have fewer camera measurements. I'm now going to set the timestamps of the out-of-sequence measurement to the timestamp of my latest processed measurement. In other words, once an OSM is detected, I manually shift its arrival time to avoid this error. The result will look like this. As we can see here, no object can be stably tracked anymore. The modification of the timestamp creates artificial camera measurements that are inconsistent with the radar measurements. Since the delay of the camera is systematic, there is constant disagreement between the two sensors' observations, and no object can be confirmed long enough. Now I'm going to try the buffering solution. The buffering is one of the algorithms implemented in the backend of Create Embedded. It can be easily enabled in the Data Fusion Designer. To do that, I will go to the menu Project, select Add a Data Fusion item, and choose the deterministic buffering from the list. To set up the buffering properly, I will also need to specify the sensor frequency and delay in the Data Fusion Designer. The system needs this information to determine the buffer size at compile time. While compile time, it's worth mentioning that Baselabs Create Embedded targets embedded systems, and the C code I have obtained is compliant with MISRA C guideline, which prohibits the usage of dynamically allocated buffers. After that, I need to regenerate the code for the newly configured data fusion system. And this gives me a new sensor fusion library, but this time equipped with the buffering mechanism. To initialize the buffer, I will need to add this function call in my code. After that, the actual invoke of the buffering is totally transparent to me. Now I'm going to start the replay again. The system operates without any problems, and the result remains plausible. A final remark is that since I have added a systematic delay in the camera measurements, the overall system has now a delay compared to the baseline. But I have ensured that the system will not process any outdated measurements. In this video, I have shown how to deal with out-of-sequence measurements with Baselab Squared Embedded. This can be caused by spikes in sensor latency. A sensor, especially a smart sensor, has normally a larger delay than the other sensors providing raw detections. Based on a simple example consisting of a radar and a camera, I first show the result with correct data, just to create a baseline. Then I tested with out-of-sequence measurement data. This issue was immediately detected by the system, which then ceased working. After that, I show 3 possible solutions to handle this OSM issue. The first solution is to ignore any out-of-sequence measurements. The second solution is to modify the timestamps of the measurement that arrives out of sequence. These 2 solutions avoid this issue but introduce artifacts, which clearly decrease the performance. The third solution, which is also the solution of Baselab Squared Embedded, is to use a so-called deterministic buffering. To enable the buffering, I did 3 things. First, in the Data Fusion Designer, I added the buffering feature. Second, I rebuilt Sensor Fusion library. Third, I initialized the buffer in the application in which the Sensor Fusion library is integrated. And then, the OSM handling works totally transparent to me. Using the buffering mechanism, all the measurements are considered and no artificial measurements are created, and the result was plausible. If you want to find out more about Baselab Squared Embedded and how you can apply it to your sensor setup, please follow this link. Thank you for watching and see you next time.